Okay, now my dilemma today is that whereas last time I had very few pages of notes, so we got done relatively quickly. Now I have way too many. So, and unfortunately, I only have today budgeted for this section. Some of the problems involve integrals, so to make sure I cover the key topics, I'm not going to go through every step of the integral here in class. It's written in the notes. You also be looking at the notes anyway. You find it there. So we'll make sure that you get like the main info you need to do the homework. So to solve out calculus with parametric curves. So we'll be looking at how to compute arc length of a parametric curve, also area of a region bounded by a parametric curve, and how to compute a tangent line, dy dx for a parametric curve. Okay. All right. So first, arc length. So we have some curve going from point A to point B. What is the length of that curve? I mean, right now we only know how to compute lengths of like line segments. What about something curved? So the idea here is if I break the curve down into several line segments, then I can compute the lengths of these line segments and add them all up to get an approximation of the length of a curve. And the more line segments I use, the more accurate my approximate length will be. So if I pick out one of these line segments and zoom in on it. So here's the curve, but I'm using this line segment to approximate its length. Okay. Then what we have here is a right triangle where this leg of a triangle is delta x and this leg is delta y. So the length of this segment is equal to square root of delta x squared plus delta y squared. So it's this idea that the basis for the formulas for arc length of a curve. So what I could do with this expression is I could factor a delta x squared out from square root sign, which actually means factoring out just delta x outside the square root sign. So this is the same as 1 plus delta y over delta x, the whole thing squared, and then we have a delta x sitting outside. Okay. That's just one segment. If I'm adding up a bunch of these, and then to get approximate length, and then letting delta x go to 0, what kind of expression is that going to lead to? Like if I'm adding a bunch of things. Yeah, so before in Cal 2 you learned about approximating area by summing areas of infinitely many rectangles. Here we're doing the same thing, except instead of integral rectangles, it's line segments. So, so this leads to 2 arc length formulas, depending on how the curve is described. if you have y being a function of x, and x is between a and b, so it's a curve that has to pass the vertical line test. The formula for the arc length, so referred to as L, is the integral from a to b of a square root of expression similar to what I wrote over there. 1 plus the derivative, so f prime of x squared dx. On the other hand, if a curve is given by x equal to some function little f of t, y is some other function little g of t, and t is between a and b. The formula comes from, if I took this expression, the first one, and I multiplied and divided by delta t. So I have a delta t sitting outside. The delta t, the denominator, I bring inside. And that's going to give me square root of dx dt squared plus dy dt squared, and then dt. You can see how this expression relates to that one, just by multiplying and dividing by dt, or delta t. Okay, and that's it. That's how you compute arc length for a given description of the curve. Now, because of a square root, these kind of integrals are generally difficult to evaluate. In fact, it's rather difficult to come up with decent homework problems where these kind of integrals can be worked out exactly using the techniques that you learn in Cal 2. So it's quite a contortionist exercise for writers of calculus books to come up with descriptions of curves so that the under these square root signs works out nicely and you can actually carry out the integral. It's almost comical. If I need an arc length, I would just go to MATLAB and have it evaluated numerically. Then I wouldn't care what the curve was. But there's some that are reasonably simple. For instance, if the curve is a line. Like in this first example. We have a curve described by y equals 2x plus 3. And x is between 0 and 2. So y prime is just 2. So the length of a curve is the integral from your endpoints in x are the limits of integration. Then we have square root of 1 plus, and then this derivative squared. Don't forget to square it. Okay. So then your integrand is just a constant. So when your integrand is a constant, and this is a definite integral, the value is just equal to that constant times the difference in the limits. So get the arc length that way. What would have been another way to get this length without using this particular formula? Because it's a line. Yeah, that you can plug in x equals 0 and x equals 2 into here to get the 2 points at the end of the segment, and then use a distance formula to compute the distance between them. In fact, I've done that in the notes and get the same result. But only possible if it's a line. Okay. So a somewhat more interesting example. So a curve described by y as a function of x, and y is equal to, oh, okay. Actually, so I start with a different equation for a curve, B. I mentioned this before, the asteroid, as opposed to asteroid, x to the 2/3 plus y to the 2/3 is equal to 1. Now, I've drawn the asteroid before. It looks like this. It's kind of like something from a Pittsburgh Steelers logo or something, like that kind of shape. Now, because of the nice symmetry, not that my picture shows it, but the symmetry of the asteroid, it's enough to pick out one of these pieces. So we get the arc length of this piece that I've circled, and then multiply it by 4 to get the arc length of the entire thing. So sometimes it's helpful to do that, to break the problem down a little bit if there's some symmetry involved. But what I would need to do is I need an equation for a curve like y as a function of x, or parametric equations. So I'll do y as a function of x. So I can solve this equation for y, and what I get is y is equal to, I'll move the x to the 2/3 to the other side, and then all of that is raised to the 3/2. Now I have y as a function of x, and x is going from 0 to 1. That traces out this segment. Okay, so now I can apply the first arc length formula to this curve with these endpoints. So to set up the integral, L is the integral from 0 to 1. And then I have a square root of 1 plus the derivative of this function. And the whole derivative is squared dx. Okay. Any questions on how the integral is set up? That's the main thing I'm focusing on, because now what's going to end up happening, and again, this is one of these contrived problems, toy problems, that if you go ahead and take the derivative using the power rule and chain rule, and then you square all of that, an algebraic miracle happens, and you end up with x to the minus 1/3. This whole thing simplifies too. And then you go ahead and use the power rule on that, and the result that you're going to get is 3/2. Okay. So that's just for one segment. So then you multiply that by 4. So it turns out that the length of the entire asteroid going all the way around is 6. All right, so the details are in the notes that how the algebra worked out after taking the derivative, but. I'll check it what there'll certainly be 1 or 2 arc length problems in the final. I don't recall if I made it as statutory or not. But well, they'll be prepared. But no, this is Cal 3, not Cal 2. So it's not my goal to have you spend half an hour on my final evaluating an integral, even though some of you might like that.
You say,
Yes,
pretty high.
by Monday. Yeah, practice test, just like the midterm. And formula sheet and all that. Okay,
And our next exam is during finals week, right?
yeah, I believe it's on the Monday of finals week,
Yeah.
get out of the way. I don't recall like what time of day it is, I mean, 2.5 hour slot.
It's like at 11 o'clock till 1.
Oh, okay, yeah. I guess the time's like 10:45 to 1:15, something like that. Yeah, it's like 8 to 10:30, then 10:45 to 1:15, and so on. Suffering never ends. Okay. Next example I'll do will be a parametric curve. So we have x is 2 cosine squared theta. Y is 2 cosine theta sine theta. And theta is prescribed to go between 0 and pi. Okay. As far as okay. Oh, I have a not well scaled picture in the notes. So it's actually, so this curve describes a circle. And radius 1. And the center is at the point x is 1, y is 0. Okay. Now, now what you can do is, actually, who can tell me what the arc length of this would be without doing any calculus? Yeah, 2 pi r, or r to radius 1, is the circumference of a circle. So at least we know what we're supposed to get. But you know, practice using the formula for arc length. So it's you go from 0 to pi of square root of dx squared plus dy dt squared dt. Okay. And so if we go ahead and take the derivatives, so dx dt, we'd have, by power rule, we'd have 4 cosine theta times the derivative of cosine, which is minus sine, and all of it gets squared. And then for dy dt, we'd have, okay, so we use product rule. So we have 2 times cosine times the derivative of sine, which is also cosine. And then we have, okay, minus 2 sine squared theta. And then we would need theta. Oops. Okay, so here, this is a generic formula. T is whatever your parameter is. In this case, the parameter is theta. So your integrals with respect to theta, not t. Okay. Now, if you leave it like this, whoops, that whole derivative is squared, forgot that. There's a couple of ways you can go with this. If you could expand out everything, and then some cosine squared plus sine squared magic happens. Because what's going to happen is this integral turns out to be integrand collapses to 2. That's trig identities for you. So sure enough, you get 2 pi because the limits are 0 and pi. Now, okay, so like I said, you could expand all this out and get it simplified this using cosine squared plus sine squared equals 1. But can anyone tell me, just looking at these expressions inside squarings, what trig identity could be used right here to get something simpler? Yes. Both double angle formulas. The one for, so this is, works out to be 2 sine 2 theta here, or minus that. And then this is the 2 cosine 2 theta. So, okay, so I'll just write that in here. The double angle formulas, and this whole thing here is minus 2 sine of 2 theta. So again, you have cosine squared plus sine squared equals 1, but with 2 theta instead of theta. So I did not use this approach in the notes, but still get this outcome. So that's how these problems roll. To some basic expression to start with, and then it just simplifies to nothing. Okay. Any questions about this one? Oh, not bad. Okay. I could do one more. So arc length of this parametric curve, x is equal to t sine t, y is equal to t cosine t, and t goes from 0 to 2 pi. Now, the way this curve behaves is because of a factor of t in both the x and y, like initially, we're at the origin at t equals 0, and it spirals out. Because sine, if it was just sine t cosine t, you'd be on a unit circle. But because you're multiplying by t, your x, y points are increasing in magnitude. So it's just going to keep spiraling forever. Okay. So we want the arc length of this curve, where t is going from 0 to 2 pi. Okay. So you need your derivatives. So for dx dt, you would need the, well, what would you need to get these derivatives, dx dt, dy dt? What rule?
Sure.
Product rule.
Oh,
Yeah. Okay. And what would that product rule give you? For dx dt?
T cosine T plus sine T.
Yeah. Okay, and for the other one?
Negative T sine T plus cosine T.
Yeah. Okay, so we can see we're gonna have a big algebraic mess. So the integral will be from 0 to 2 pi square root of this derivative and all that squared plus this derivative squared. Wow, that's a really chaotic square root sign. Squared dt. Okay, and what will happen if you FOIL these out? As you can expect, a lot of sine squared plus cosine squared equals 1 is going to happen. It doesn't collapse to a constant this time. But you do get something similar, 1 plus t square root of 1 plus t squared dt. But this is still a pain. What approach could you take for an integral like this? Yes, which substitution should I make? Yeah, t is equal to tangent of theta. All right, so then dt is equal to secant squared theta, and this square root expression, what does it become? The square root of 1 plus t squared. Well, the overall integrand will be secant cubed. Yeah, just this by itself is secant. And that combined with dt, so you end up with integral of secant cubed. And yikes on bikes of that one. Okay. And yeah, when it's an odd power of secant, okay. And unfortunately, I don't have it fully written out in my notes exactly how it's done. But that's what I remember. But when it's an even power of secant, that's a lot easier. You can write things in terms of tangent. Use substitution. So what you get is the integral from the limits change. So we have. Well, I'm going to ignore the limits, focus on the indefinite interval, because then you can just change back to t after. So secant cubed theta d theta. So if you're doing integration by parts, make sure that the dv is something that is easily anti-differentiated. For example, secant squared. And then here we have, so then u would be secant. Du would be secant theta tangent theta, and then d would be tangents. So then you have u times v by the integration by parts formula minus the integral of v du, which gives you secant theta tangent squared theta.
Is that a different problem or just different or something?
No, from this, making this substitution, you get secant theta from here, dt produces secant squared, and that brings us over here. Okay. Yeah. All right. Now, things get very dicey from here. You write the tangent squared theta as secant squared theta minus 1. And then you distribute. So now you have, we should be spending this much time on this, but this is a trick that comes up now and then, and I want you to be aware of it. So distributing, I get minus integral of secant cubed theta, which is where I started. And then I have plus integral of secant. Now, before you think you're going around in circles, you keep in mind that, okay, we have the same integral on the right as we started with, except with the opposite sign. So you take this and you move it to the other side. And now you have two of them on the left side. So you can just divide by 2. So now what you have is the integral of secant cubed theta d theta is equal to 1/2. I mean, you have secant theta, tangent theta that was there before, plus the integral of secant, which can then be worked out. Natural log of secant theta plus tangent theta, and then this would be, so then this would be written, rewritten in terms of t. Okay. Now, okay. Now, as far as converting back to t, use the fact that tangent theta, that's just t itself. And then secant theta is square root of 1 plus t squared. So you make those substitutions throughout. Now it's back in terms of t. And you can plug in the original limits in t, which were 0 and 2 pi. And that's carried out in the notes of those last steps. So the only thing I didn't have in the notes, but I can add it later. Is
Sorry.
the integration of parts part, yes.
Yeah, so after the 1/2 there, is that an integral symbol or is it a bracket?
This right here,
Yeah,
that is bracket,
got it.
matching this bracket.
Yeah, just wanted to make sure.
Yeah. Okay. Okay. So that's how arc length problems are. We're getting obnoxiously simple integrals after a lot of algebra or trig, or integrals from hell, like this one. Any questions about what we saw in this? Yes.
We have to know how to do all that.
No, I'm more interested in, what formula to apply, how to set up the integral. That sort of thing.
So we can use a calculator.
Yeah, or I may give some integration formulas, like a formula sheet, so. But I'll take this into account when I set the problems for final, but again, I don't want to be spending a lot of time working on an integral. Okay. All right, so that's arc length. Another problem is computing a tangent. You know how to compute a tangent line for y equals f of x, it's just dy dx. But if it's a parametric curve, and I mentioned this last time, but I'll lay it out now. Okay. So if you're given parametric curves, x and y are both functions of t, then and you want dy dx at a certain point. So that could be expressed as dy dt divided by the x dt. So informally, at least, you can think of it as the dt's canceling out. Okay. Okay. So so as an example, Let's suppose the curve is one from a previous example. X is equal to t sine t, y is equal to t cosine t, and the derivatives of those were worked out earlier. So dy dx equal to dy dt over dx dt. So we can fill in what those were from before. I'll just repeat the product rule. So we have up top minus t sine t plus cosine. And then down below we have a derivative of x. So that's t cosine t plus sine t. So suppose you were asked for the tangent line at the point x is pi over 2 and y is 0. Well, if you're given xy coordinates of a point of tangency, you need to know what t value does that correspond to. What value of t would produce this x and this y? No?
Oh, wait.
Anyone?
Zero.
That would give you 0, 0. Let's t value 1, one's not a nice angle. The sine or cosine of 1 aren't anything in particular. But since what y to be 0, we'll focus on what angles cosine is 0 at. Yeah, let's take one of those, pi over 2. That would make y 0. If what happens, what's sine of pi over 2? 1. So you multiply that by t equal pi over 2 and you get pi over 2. So pi over 2 is the correct t value. So then what you can do is you can substitute that in here to get the slope. So the slope m is equal to minus pi over 2 sine pi over 2 plus cosine pi over 2 divided by pi over 2 cosine pi over 2 plus sine pi over 2. Now cosine of pi over 2 is 0, so a couple of those terms are going to go away. And once you simplify everything, you end up with minus pi over 2. So to get the tangent line, you can, easiest way is point slope form. Y minus the given y value, which is 0, is equal to the slope times x minus the x value, which is pi over 2. So this is an equation for that tangent line of the curve at that point. Any questions about this one? Okay, now we have a relatively simple formula for dy dx, but what we also like to have is concavity at a point. So what is the second derivative of y with respect to x? So if we go back here, okay. So second derivative of y with respect to x, which is the same as taking dy dx and taking its derivative with respect to x. Okay. But looks like I have a mistake here in the notes. Do I? Oh, okay, never mind. Now, if I go ahead and compute dy dx using this formula, I have dy dx as a function of t. But now I want to differentiate with respect to x. So I can think of this in terms of differentiating with respect to t. And then I multiply that by dt dx. But I don't have dt dx. Instead of multiplying by dt dx, what can I do instead with what I do have? Because I have these available to me. Okay, so multiplying by dt dx is equivalent to for the purpose of this question, you're welcome to think of dt dx as a fraction.
So the inverse. Yeah.
Yes, okay. Okay, you said yeah, but being what? Elaborate.
The inverse of the dx with you.
Yes. So this is the same as dt dy dx divided by dx dt. Yeah, so yeah, so multiplying by, so instead of multiplying by that, you divide by its inverse. Okay. So if you've already gone into trouble computing dy dx as a function of t, now you can go ahead and differentiate it with respect to t, no problem. You just have to divide by dx dt afterwards. Okay. I just realized, yeah, in the notes in this formula, I have a mistake that it says x where it should be t, but I'll correct that on Canvas. I have another formula for dy dx that's more fully worked out using a quotient rule, but it's easier to just do this. Okay. No. So to illustrate this, we'll look at where we've seen a couple times already, the asteroid. Okay. So we have parametric equations. X is cosine cubed, y is equal to sine cubed. Okay. So we want to find out. Asteroid. Where is the asteroid? Concave up or concave down? And here we have a graph. Okay. Of course, you can answer right from the picture, but let's go through a process to illustrate the mechanism. Okay, so we first do dy dx. That's dy dt over dx dt. All right, so what is dy dt?
Square t times cosine t.
Yeah, 3 sine squared cosine t. All right, and down below,
3 cosine squared t times sine t.
okay. So we have some cancellation happening. The 3's cancel. We have sine. There's a sine canceling from one of these. This cosine canceling from one of these. So you end up with minus tangent of t. After you cancel everything that you can. And that's nice because for a second derivative, we gotta take the derivative of this with respect to t. And now that's, don't need a chain rule or anything. Wrong thing. Okay. So the second derivative of y with respect to x, you take derivative with respect to t of the dy dx we just got, this minus tangent of t. And then we're going to divide that by dx dt, which is what we have down here. But what is the derivative up top? Secant squared t over minus 3 cosine squared sine squared.
Is it negative?
Yeah. Okay. All right, so secant squared upstairs is the same as cosine squared downstairs, which multiplies with the other cosine squared that's already waiting for us downstairs. So you get 1 over 3 cosine to the 4th times sine. So now we need to see where is this positive or negative. Well, much of this fraction is already guaranteed to be positive. The only thing that could be positive or negative is a sine t right here. Well, sine is a y-coordinate of a point on a unit circle. So, so sine is positive when y is positive and negative otherwise. So this is positive for y positive and it's negative when y is negative. And we can see that from a picture here that the 2 segments above the x-axis are concave up, the 2 below are concave down.
So how did you get the 1 on top?
Oh, so minus secant squared t is the same as minus 1 over cosine squared t.
Goes down.
Oh, okay, so it's okay.
Yeah, that's right, I got 4 of them here.
How did you simplify to the negative change?
Okay, gone, that one's gone, and that one's gone. So then you have a sine up top and a cosine down below. Yeah. Other question? Okay. I just have time for the remaining topic, and that is area under a parametric curve. More integrals. So there are some examples from arc length and tangents that are in the notes that I haven't covered here. But I recommend looking at those. Okay. Now, what you're familiar with is we have a region like this that is bounded below by the x-axis, bounded above by some curve y equals f of x. Then we have left boundary x equals a, right boundary x equal to b, that the area of this lightly shaded region is given by what? Integral of what? Yeah. Okay. So we know how to do this for a case of a curve described by y equals f of x. All right. Now, let's look at different scenario. Same kind of region though. So we're still looking at area above the x-axis, but now the curve in question is described by x is equal to little f of t, y is equal to g of t. So that top boundary is now described parametrically instead of y being a function of x. Okay. And for t, ranging between two boundary points, boundary values alpha and beta. And very important, alpha and beta need to be chosen so that the curve is traced only once. We've seen cases of parametric curves where you go around the circle again and again, something like that, or maybe going back and forth. So we're just tracing out the curve one time. Okay. Then, so in that case, and whatever x value you have here and here still serve as boundaries. So we're still computing the area of the same region. It's just that part of the boundary of this region is described differently. Okay. Now, so we still have these boundaries called x equals a and x equals b. Now, how you get the area, there's two slightly different formulas depending on the orientation of a curve, in what direction is it traced out. So if f of alpha is equal to a and f of beta is equal to b. So in other words, the curve is being traced out from left to right. Okay. Which also indicates that dx dt for most is has to be positive when that's happening. Because t is going from left to right, x is also going left to right. So in that case, the area, I get to work with this integral, but keep in mind that this right here, this f of x is y. So I get the integral from alpha to beta dt, and I have y, which is g of t, and then dx is the same as x prime of t dt. So I'll have f prime of t dt. So that's the formula for area under the curve in this situation. But now we're going the other way. if f of alpha is equal to b and f of beta is equal to a. So the curve is being traced from right to left. In other words, dx dt is negative. Then the area is, you actually have the same integral, but from beta to alpha. The same integrand. Or if you want, you can, if you really want to have an integral from alpha to beta, you can do that. You just switch the limits and that negates the sign. All right, so you have to be careful about how the curve is being traced out. So now I'll illustrate with an ellipse. A badly drawn ellipse. Okay. So, well, the ellipse has parametric equations. X is equal to a cosine theta. Y is equal to b sine theta, where a and b are not equal, otherwise it would be a circle. And the entire ellipse is traced out by taking theta from going from 0 to 2 pi. Okay. But if we're going to use the area formula, we have to keep in mind what we're getting the area of. It's area between the curve and the x-axis. So what I'm going to do, because of the symmetry of the ellipse when it's properly drawn, I'm going to focus on getting the area of this shaded region here. And then I'll multiply by 4. So when theta is equal to 0, x is equal to a, and y is equal to 0. So this is a point A0. This is for theta equals 0. Okay. Now, so now I know what theta value corresponds to this endpoint, which would be by rightmost x value. I want this leftmost x value. So I need the theta value for that point. And so this is the point where x is equal to 0 and y would be equal to b. But what theta value is that?
93 or
Yeah. Pi over 2 radians. Yeah. So I'm going to have an integral from 0 to 2 pi, no, not 2 pi, integral from 0 to pi over 2. Okay. So the area of just the shaded region, integral from 0 to pi over 2, and which formula of the two that I have here is the one that I need in this case.
The top one. Oh, wait, it's not left to right anymore.
Yeah, it's right to left. It's this one.
Yeah.
Okay, so we're gonna have a minus, and then we have our y function, so that'd be b sine theta times the derivative of our x function with respect to theta. That's gonna be minus a sine theta. Okay, so the minuses cancel out, which is good because we expect a positive result for area, generally speaking. So now I have, well, AB, that's a constant, I can pull it out. And I have sine squared theta d theta. But in order to integrate sine squared, what do we need to do to that to be able to integrate it? Anyone? We need to rewrite it. Somebody? This hasn't come up. Half angle formula. Okay. So sine squared theta is equal to 1 minus cosine 2 theta all over 2. And that is something that can be integrated. So we have AB, and then we have 1/2, that's going to be theta over 2, minus sine of 2 theta over 4, because we're already divided by 2. When you integrate cosine 2 theta, that introduces another factor of 2 in the denominator, and that's what limits 0 and pi over 2. But when you plug those limits into the sine part, you're gonna get 0 no matter what. This is not going to contribute anything. So you end up with AB times this theta value over 2, so pi over 4. And that's the area of just the shaded region. So then the area of the ellipse, the entire ellipse, is pi AB. Which one was good enough formulas anyway? It all makes sense because if, like I said, if A and B were equal, you'd have a circle of radius being a common value, pi r squared. But I'm thinking the same. Pi are not squared, pi are round, cornbread are square. All right. We're almost done. Okay, any questions about this one? The half angle formula seems to come up surprisingly often, so definitely something good to be aware of.
That is 2 theta, right?
Yes, yeah, 2 theta here and here. Okay. Last example. Okay. So find the area of this region of these boundaries. All right, so we have boundaries of y equals 1, x equals 0, and then the curve with parametric equations, x is equal to cosine of t, y is equal to e to the t, and t goes from 0 to pi over 2. Okay. So, to be able to do this properly, or even to use the right formula, need to have an idea of what a region looks like. All right, so x equals 0 is one of our boundaries, but we also have y equals 1. So you have to take that into account. Okay. Now, as far as this curve, when t is equal to 0, where am I at in the xy plane? Yeah, if t equals 0, where am I at in terms of x and y?
1.
Yeah, 1, 1. So, okay, this is totally not the scale. Yikes. Okay, so that's the starting point for our curve. In other words, we're going from right to left again. And where are we at when t is equal to pi over 2? Mm-hmm. 0 and nothing special. E to the pi over 2, which is the short of 5. So it's up here somewhere. So the curve behaves something like this. So this is the region we want the area of. Okay. Okay. Now, because we're going from right to left, we're going to use the second formula from before, the minus the integral from 0 to pi over 2 of y times dx dt, which is what? Yes.
Negative sine t.
Yeah. Okay. But they don't tell me why. Well, this is a valid formula for the area of a region. It's not the area that we're actually looking for. Yeah.
The boundary.
Yeah, boundary is y equals 1, not y equals 0. This would take me all the way down to the x-axis. So that's no problem. I just have to,
Find that area.
yeah, subtract that off. Well, what would that area be? One, because it's from 0 to 1 in x and 0 to 1 in y. It's a square. I know it doesn't look anything like a square, but
yeah.
But in Euclidean space, which is not what I have on the board at all, it's 1. So we just go ahead and do the integral, and then just need to subtract off 1 when we're done. Okay, so cleaning this up a little bit, so we have an integral from 0 to pi over 2 of e to the t sine t dt, and then we subtract 1. Okay. How would you do an integral like this?
Just using integration parts until you, like sine becoming cosine.
Yes.
So you
Um,
will add.
Yeah, so what will happen is if you apply integration by parts twice, you'll end up with another integral involving e to the t sine t, which you move over to the other side. So it's similar to what happened a couple examples ago. Okay. And so this turns out to be 1/2 plus 1/2 e to a pi over 2, and then you subtract 1 off from 1 from that. You get the final result. Okay. And I won't go for the individual parts there because of time, but there actually is a somewhat easier way to compute the area of this region, because although we do not have y equals 0, the x-axis as a boundary, we do have the y-axis as a boundary. So if we reversed the sense of y and x and y, which are reversed roles. So what we could do is, so an alternative area is integral of x dy instead of y dx. So, okay, so x is cosine t. And then I want dy, so y prime, but y is e to the t, so y prime is also e to the t. Yeah, I guess the actual integral itself isn't easier, but we don't subtract anything off though, which doesn't mean much at all. But as far as the limits are concerned, well, the limits would still be 0 pi over 2. All right, so that's never know, might be helpful. Okay, so all right. Any questions about everything that transpired here?
In this situation, since t is bound, using the y-axis doesn't change our a and b.
Oh, okay. So what happens in this case? Okay, so when t is. Okay, since t is 0, we're here. And. Okay. Okay, what's different here, are you asking me to negate? Or,
No, just like the limits, 0 to pi over 2 doesn't change because.
because we're still using, yeah, because we're still describing curves as a parametric equations involving t.
Okay.
Yeah. Yeah. Okay, but what I thought your question was about, it's still worth pointing out. We did the original way, we're going from right to left, but when we change perspective, going along, integrating x dy, now we're going from bottom to top. So there's no need to negate. So in that case, so what's happening is as t increases, y increases. dy dt is positive, so you don't negate. Okay. Any questions? All right, next week, polar coordinates. Woo. Almost over.
I'll make it, I know it.